Hello viewers, Wagadaruna taking you through the story for A-Level Physics Paper 1. And this video we are going to go through the marking guide for U.A.C.E Uneb for the year 2022. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So what is ticked is what is available on this platform, and today we are going to go through this marking guide for A-Level Physics Paper 1. So these books are available and may be very helpful if you are in A-Level. So in math there are 4 books: Principal Math, there's Math 1, Math 2, Topical Question Bank, and Termly Past Papers. Submath is only 1 book, and for physics there are also 4 books: Physics 1, Physics 2, Topical Questions, and their solutions. So for copies, I encourage you to call this contact so that you get them at a relatively cheaper price. Otherwise, they are there in bookshops, but the price may be a little higher than what you would buy them if you called this contact. So in physics, they usually give you constants which can be used where necessary. So every paper of physics has those constants. That's the continuation of the constants which can be used in the calculations. So now we shall go to questions. So remember, a paper contains 3 sections and 10 questions. So section A is entirely on mechanics and has 4 questions. That's what we shall begin with. So all the 10 questions will be answered. So question 1 part A says, define the following: Roman 1, brittleness, and Roman 2, elasticity. So brittleness is the ability to break suddenly. So you can either use the word suddenly or easily when a force is applied. What about elasticity? Elasticity is the ability of a material to return to its original shape, size when a deforming force is removed. So it has to return to its original shape and size. That was part A. Then part B. Part B says state Hooke's law. So Hooke's law states that the extension of a material is directly proportional to the force causing it, provided elastic limit is not exceeded. So this last condition is needed. Elastic limit must not be exceeded. And that's how you can obtain the marks for those parts. Then part C now. Part C says, figure 1 shows graphs of stress against strain for 2 metals X and Y. State and explain which metal, Roman 1, has a greater Young's modulus. Roman 2, which metal is more ductile. And Roman 3, which metal is stronger than the other. So they want you to state the metal and also give a brief explanation. So for Roman 1, we shall say metal X has a greater Young's modulus. So the question is why? This is because it has a bigger slope. You can either say bigger slope or bigger stress-strain ratio for the linear part of the graph than metal Y. Let's analyze it and see if it is true. So if you look at this, for the linear part up here and also up here, this slope is bigger than this. Therefore, it has a bigger Young's modulus. Remember, the slope will be the Young's modulus, because Young's modulus, by definition, it is stress over strain. Okay, then Roman 2 was, which metal is more ductile? So you have said that metal X is more ductile. And the question is, why? So this is because the plastic region of graph X is greater than that for graph Y. So that is why it is more ductile. So I think you know the plastic region for metal. If you look at this and this one is bigger. And it is above. If you see this, the stress is higher. Then which metal is stronger than the other? We shall say metal X is stronger than metal Y. And why is it so? It is because metal X can withstand a greater stress before it breaks. So is it true? Let's also analyze that. For this to break, the stress will be here, and for this to break, the stress will be here. So this stress is bigger than this, meaning it is more stronger. Then part D Roman 1. D Roman 1. So D Roman 1 says, two wires P and Q of the same length, of the same material, have equal lengths, but the radius of P is twice that of Q. Which wire, Roman 1, can withstand the greater load before breaking? And Roman 2, which wire has the greater strain for a given load? So for Roman 1, we shall say, where P can withstand a greater load before breaking. And why is it so? This is because it has a greater cross-section area. It has a larger cross-section area than wire Q. Then Roman 2, we shall say, wire Q has the greater strain for a given load. And why is it so? It is because it will have a longer extension for a given load. So that's how marks would be awarded. Then we shall now go to part E. Part E says, a copper wire of length 4 meters and cross-section area this is fixed between two rigid supports A and B, 4 meters apart. What mass, when suspended at the middle of the wire, will produce a sag is like a depression of 1.5 meters at that point? Then they told you to take Young's modulus of copper as that. So this is the calculation. Let's see how we can deal with it. First, we shall make a simple sketch to interpret the information given. So they said the mass here, when it is put, there will be a sag of 1.5. And they said these points are 4 meters apart. So let the mass be of weight M. Because of this M, there will be tension in the string. Now, why is this tension the same? It is because it is still the same string. As long as the string is the same, tension will be the same. So this sag will, this angle is theta, we just call it theta. They'll help us to resolve. Now this AB is 4 meters, that's what they told us, meaning AO is half, and this. Then also OC is 1.5, which was the sag. Meaning I can easily get the value of theta by saying tan theta is equal to opposite over adjacent. Opposite is 2, adjacent is 1.5. Use a calculator, angle will be 53.13. So angles are to 2 decimal places. Then from Pythagoras theory, AC is equal to BC and can be got from any of the 2 right angles. So if I use this, it means I'll use this plus this, which is 2 squared plus this 1.5 squared. Everything under square root, the value will be 2.5 when you use a calculator. Then the new length will now be SC plus BC, which is this plus this, to give you 5 meters. So the new length and minus the original length gives you the total extension, which will be 1 meter. Therefore, the tension is given by this formula, which is got from stress over strain. So capital E is Young's modulus, cross-section area, extension, original length. So come and substitute. Young's modulus was given as a constant, cross-section area was given, extension, you have got it. Then original length was that. So use a calculator and that will be the answer, the tension in the string. Then resolving vertically, you'll come up with 2t cos theta equal to mg. Then substitute for t, for theta, and for g. In physics, g is 9.81. You'll be able to get the value of m, and that's what they wanted. So that's how the marks would be awarded. Now we shall go to part F. Part F says, explain why water flowing out of a small hole at the bottom of a wide tank results in a backward force on the tank. So one we shall say water acquires a velocity, or which we call velocity of efflux, as it moves out. Therefore, it has a forward momentum, so the tank should acquire an equal and backward momentum in the same time, hence a backward force. So this is in accordance to Newton's third law. So that was question 1. Remember, in Uneb writes reports after every marking session. So this is the report they gave for this question. So the report is for every question. They analyze what the question required, the weakness, and the advice. So here the question required you to state Hooke's law, define brittleness and elasticity, then compare ductility, strength, Young's modulus, and also getting Young's modulus, given the data, and stress strain graph. So the weakness is that candidates lacked knowledge about the concept of mechanical properties of matter. So the process of preparation, you need to fully understand the topic. Then failure to interpret the stress strain graph for 2 metals. So advise that encourage students to read recommended textbooks by NCDC, and teachers should teach concepts about mechanical properties of matter extensively. Practically demonstrate some of those mechanical properties of materials. and relate teaching physics to solving day-to-day problems. Then now shall go to question 2. Question 2, part A, Roman 1 says, what is meant by dimensions of a physical quantity? So dimensions of a physical quantity is the way that given quantity is related to the basic or fundamental quantities of mass, length, and time. So you can either use the word basic or the word fundamental. Any of the two is okay. Then Roman 2 says the velocity v of a wave of wavelength lambda on the surface of a liquid of surface tension this and density this is given by this, where g is the acceleration due to gravity. Show that the equation is dimensionally consistent. So that is what was given. So we shall get the dimension of each. This dimension, remember this was velocity, dimension is that, but it is squared. So end up with this. Then for this one, this is wavelength, which is that, acceleration due to gravity. This is a constant, so it is 1. So end up with this. Then this one is also, this is a constant. This one is here, surface tension, wavelength, density. So you come up with this, which gives you that. Therefore, you realize that all of them are equal. Therefore, you can conclude. So each time there is plus or minus, it means this dimension must be equal to this for it to be dimensionally consistent. So now shall I go to part B. Part B says figure 2 shows acceleration time graph for a body of mass 10 kilograms, which starts from rest and moves in a straight line. Use the graph to find Roman 1, the distance traveled in 15 seconds, and Roman 2, the average force acting on the body over 15 seconds. So for the first 5 seconds, acceleration is 2. Then for the next 10 seconds, acceleration is 0. That's what this graph means. So for the first 5, acceleration is 2, time is 5, u is 0. So use the second equation of motion and substitute for u, for acceleration, and for time to get 25 meters. First equation of motion, u, acceleration, time to get the final velocity after the 5 seconds. Then for the next 10 seconds, initial velocity now becomes this. Acceleration is 0, time is 10. So using second equation, initial velocity, time, acceleration, time. So we'll come up with that as the distance. Therefore, total distance covered is got by adding the 2 to give you 125. Then Roman 2, the one, the average force acting on the body over the 15 seconds. Average force is given by this formula, mass times the average acceleration, which is m times change in velocity over time. So m is here, change in velocity is that, and total time taken is that, which gives you that as the force. And that's how marks would be awarded. Then part C says, With examples, explain any two of Newton's laws of motion. So first we shall say, every body continues in its state of rest or uniform motion in a straight line unless it is acted upon by an external force. So that is the law, but they told us to give an example. So an example is a person in a car jerks forward when the car suddenly stops. Then the next second law is the rate of change of momentum is directly proportional to the applied force and takes place in the direction of the force. They also ask for an example. So for example, water jet falling on the ground eventually digs a hole. Then the third law, action and reaction force are equal but opposite. And then example, a book placed on top of a table keeps on top of it. Why? Because there is action and reaction force which are equal and opposite. Then part D Roman 1, state the principle of conservation of linear momentum. So the principle of conservation of linear momentum states that when two or more bodies collide, their total linear momentum is conserved provided no external force acts on them. That last condition is very, very vital. Then part D Roman 2. A particle of mass m1 moving with a velocity u1 collides with a stationary particle of mass m2. The collision is elastic, and the velocities of m1 and m2 after impact are this and this respectively. So this is for m1, this is for m2. If the particles move in the same direction and alpha is equal to capital M2 over M1, show that U1 is given by that. So by conservation of linear momentum, we have this M1 U1 is equal to M1 V1 plus M2 V2. So remember the mass M2 was initially stationary, so its velocity is 0. That's why it is not included for the initial momentum. Then dividing throughout by M1, we will come up with this. Why do we divide by M1? It is because the alpha which was given, if you look at this alpha which was given was M2 over M1. So M1 was a denominator. That is why we chose to divide by M1. So we can easily substitute for alpha. Therefore, when we substitute, we shall come up with this expression. Make V2 the subject, you come up with that and call it equation 1. Then by conservation of kinetic energy, why? Because the collision is elastic. So we shall come and say that a half m1 u1 squared is equal to a half m1 v1 squared plus a half m2 v2 squared. So this a half can go away and also divide throughout by m1 to come up with this. Then you replace this with alpha. V2 squared, make it the subject, you'll come up with this difference of two squares, which gives that. Now we have here V2 and also here V2 squared. So I can substitute equation 1 into equation 2. When I do that, I'll come up with this, where there's V2, I'll put there this. And I realize that here the alpha can cancel, and also 1v minus u1 minus u1 can cancel. So I remain with this. And here this was going to remain with this. Now here, this one, remember it was squared, so one of it went and one will remain. Then you cross multiply to come up with that. Collect like terms, u1 this side and v1 this side. Factorize u1 here, factorize v1 here. Therefore, u1 making the subject, you'll come up with that, and that's what they wanted. Then the report is this. You can pause the video and try to read through so I don't make the same mistakes. Then question 3, part A Roman 1 says, state Bernoulli's principle. So Bernoulli's principle states that for a non-viscous, incompressible fluid undergoing steady flow, okay, the sum, so these initial conditions are needed: non-viscous, incompressible, steady flow. The sum of pressure, kinetic energy per unit volume, and potential energy per unit volume is always constant at any point along the streamline. That was Roman 1. Then Roman 2, explain with the aid of a diagram why air flows over the wings of an aircraft causes a lift. So they said with the aid of a diagram, so we shall draw a rough sketch of an aerofoil moving in that direction. That means that air will move in the opposite direction. That is air above the wing and also air below the wing. Now when you're drawing, you should be keen. The spaces for the air above and the spaces for the air below must be different. The space for the air above must be small than those for the air below. So from the diagram, air layers on top of the aerofoil move at a high velocity, hence a low pressure is being exerted here. So there is low pressure. And in the same time, air layers below the aerofoil move at a low velocity, hence a high pressure is being exerted. So high pressure means high force, meaning that the force above is bigger than the force below, meaning the force, there will be a lift. And that's how marks will be awarded. Then part B, Roman 1. Part B says air flows over the upper surfaces of an aircraft wings at a speed of 135 meters per second and past the lower surfaces of the wing at a speed of 120 meters per second. Roman 1, calculate the pressure difference due to the flow. And Roman 2, determine the lift force of the aircraft on the aircraft if the total wing area is 20 meters squared assumed density of air is 1.2 kilograms per cubic meter. So let's start with the pressure difference, after which we shall go to the lift force. So from Bernoulli's equation, this is what we have for horizontal motion. If there was vertical motion, then there will be also potential energy per unit volume. So pressure difference is you bring this on this side and bring this on the other side. So you come up with this equation. Therefore, substitute a half is here, density is here, V2 is here, V1 is here, which gives you that as the pressure difference. Then Roman 2, they want the lift force. Lift force, you multiply cross-section area by the pressure difference, which gives you that. So that's how marks would be awarded. Then part C, says what is meant by streamline flow? So shall come and say that streamline flow is a type of fluid flow during which fluid particles at equal distance from the axis of flow move with the same velocity parallel to the axis of flow. Then Roman 2 says, with the aid of a labeled diagram, describe how the velocity of fluid flow can be measured. So shall come and draw a labeled diagram to help us go through the description. So you have this manometer to record pressure P1 and this is velocity V1 at this point. Manometer to record pressure P2 and this is velocity at that point. That's the direction of fluid flow with density rho, and this is a uniform tube. So before I go to the next slide, let's first see the marks for the slide. So from the diagram above, if P1 and P2 are the pressures and V1 and V2 are the velocities of the fluid at X and Y on the same horizontal level, then from Bernoulli's equation, we have this, implying that pressure difference is equal to that. Now, if A1 and A2 are the cross-section areas at X and Y, it implies that this is equal to this equation of continuity, where V2 can be got from here. So substituting equation 2 into equation 1, we come up with this. So factorizing out V1, we come up with that. So the velocity V1 of the fluid can thus be got from the above expressions. Because these ones, you know them from the manometer. These ones, you know them. This density, you know it, meaning you can get V1. And that's what they wanted. So a student can choose also to use the pitot static tube. It is still okay. Then part D, says the depth of water in a tank of large cross-section area is maintained at 2.0 meters. If the water emerges out of the tank continuously through a hole of diameter 5 millimeters, drilled at a height of 10 centimeters above the base of the tank, Calculate Roman 1 the speed at which the water emerges from the hole, and Roman 2 the rate of mass flow of water from the hole. So H1 is this, H2 is that, which convert to meters, D1 is that, convert to meters. Then from Bernoulli's equation, this is what we have. Now you have added potential energy because of difference in height. So for a small hole, this velocity is much smaller than this, implying that it approximates to 0. And also pressures are the same. Therefore, this will go, and also this V1 will go. So remain with this alone, and you remain with this and this. Therefore, V2 is given by this expression, so substitute for G, for H1, for H2. You'll come up with this as the velocity. Then Roman 2, the rate of mass flow of water from the hole. So mass per second is density times area times volume times velocity. So density is that, area is that, pi d squared over 4, and velocity is that, to give you this as the mass flow rate. So that's how marks would be awarded. And that will be the question analysis for this question. You can pause and go through it. Then now we shall go to question 4. Question 4 part A Roman 1 says, define angular velocity. And Roman 2, explain why a body moving with constant speed along a circular path has an acceleration. And Roman 3, derive an expression for acceleration of a body moving in a circular path of radius r with a constant speed v. So let's start with Roman 1. So Roman 1, we shall say that angular velocity is the rate of change of the angle of a body moving in a circular path. Then Roman 2, a body moving in a circular path with a constant speed has a varying velocity due to continuous change in direction. Therefore, the body is accelerating. And that's what they wanted. Then for Roman 3, they want us to derive something. Derive an expression for acceleration of a body moving in a circular path of radius r with constant speed v. So I need to draw a diagram to help us derive. Then at point A, the body has this velocity in that direction. At point B, the body has that velocity in that direction. And the small angle it makes from A to B is that. By geometry, this angle is the same as this. So I can resolve that velocity horizontally to give you this, and vertically to give you this. So centripetal force is acceleration along OA, because it has to be towards the center. And acceleration is the limit as t tends to 0 of change in velocity over change in time. So change in velocity here, for vertical there is this, and here it's entirely horizontal, meaning vertical component is 0. That's why you see 0 here. So as t tends to 0, this sign of small angle tends to a small angle. Therefore, we'll come up with this, where the sign small change in theta will get small change in theta. But this is equal to angular velocity from the definition we saw in Roman 1. And we know that V is equal to R omega. Therefore, we shall come and substitute for this, which is there, and also for omega, because here omega is V over R, which is this. So in the end, we come up with V squared over R. So that's the derivation they wanted. Then part B define the following: projectile motion and angle of projection. So projectile motion is the motion of a body that moves freely under gravity after being given an initial velocity. So angle of projection is the angle in the direction of projection. Is the angle the direction of projection makes with the horizontal. That was part B. Then part C. A body P is projected vertically upwards from the ground with a speed of 36 meters per second. If object Q is dropped vertically above P from a height of 90 meters above the ground, after 2 seconds, find Roman 1 the time when P and Q collide from the time P was thrown upwards. Then Roman 2, the height above the ground where P and Q collide. So let's start with Roman 1. We shall need to make a simple sketch. So that is P being thrown up, and we have Q being dropped. Dropping means velocity is 0. So when they move, they will collide at this point, and let the height from P be S1 and from Q be S2. Therefore, using the second equation of motion, for body P, I'll have U as that, and G is 9.81. Then for body Q, U is 0, and the time, remember that this one was thrown 2 seconds later, so it will be T minus 2. Now those are two equations, but they told us when you add these two, you'll come up with 90. So before I go to the next slide, let's see the maths for this slide. So substitute for S1 and S2 and equate to 90. So next we'll simplify. This gives this, this gives this, then squaring this gives that. Then open the entire bracket to come up with this, then collect like terms. You realize that this and this cancels. Then this with this gives you this, and this is here, this is here. Collect like terms again, take this on this side, come up with that. Then make T the subject, and that will be the answer. Then Roman 2, they ask for the height above the ground where P and Q collide. So from equation 1, S1 will be given by this when substitute for T. Then also So that's how the marks will be awarded. So this is the report for that question, analysis for the question. Then question 5, part A, define the following. Roman 1, specific heat capacity, and Roman 2, specific latent heat of vaporization. So specific heat capacity of a substance is the quantity of heat required to raise the temperature of 1 kilogram. When you see the word specific, mass should be 1 kilogram of a substance by 1 Kelvin. Then specific latent heat of vaporization is the quantity of heat required to change 1 kilogram mass of a substance from liquid state to gaseous state without change in temperature. So that was part A. Then part B, with the aid of a labeled diagram, describe an experiment to determine specific latent heat of vaporization of a liquid. So here they did not specify whether you use electrical method or method of mixtures, meaning that any of the two is okay, and we are going to look at both of them. So let us start with the electrical method. There we shall need a diagram. So that is the circuit for a heater, which will heat the liquid. So we are going to connect a heater on that electric power supply. So what you should realize is that there is no switch here. Why? Because some students, they forget to close the switch. So it is advisable not to put a switch. Why? Because throughout the experiment, the switch must be closed. So that will be the water which will be heated, boiling liquid. Then you shall need a thermometer to measure the temperature. We have to put an outlet where the vapor will pass, because we have to collect the vapor. So vapor jacket. So make sure you lug so that it doesn't escape. So the vapor, that is the outlet. So vapor will pass there and move downwards. But here it has to be cooled, so we need a Liebig condenser. Which has water in from the bottom and coming out from the upper part. Then you shall need a container to collect the water, condensed water or condensed vapor. So that is the diagram. So we shall now start and say that power is switched on and the liquid is heated until it boils. This is the liquid heated until it boils. A stop clock is started and mass M collected in time t is noted. The mass here of water collected in time t is noted. The ammeter reading V1 and voltmeter reading V2, ammeter reading I1 and voltmeter reading V1 are recorded. So at steady state, I1 V1T is equal to M1L plus H, where H is the rate of heat loss to the surrounding. So the rheostat is adjusted and to obtain a new ammeter reading I2 and voltmeter reading V2 and the mass M2 collected in time T. That means that I2 V2T is equal to M2L plus H. And from there, we're making L the subject, we'll come up with this, where L is the specific latent heat of vaporization. So that is the electrical method, but you can also use the method of mixtures. So let's look at the method of mixtures. There you also need a diagram. So it has to be heated from this side and goes here, the vapor comes here and it reaches this side. So that is lagged to prevent heat loss. Then this is the heat shield, so that heat doesn't just cross over. So is the direction of the motion of the vapor. So we have this heat, we have specimen liquid, we have a flask, vapor flow, heat shield, stirrer, lagging, vapor trap vessel. I think you realize that here it is a little up so that here the condensed water doesn't go, it just falls down. Then that is the thermometer, insulator, specimen liquid, calorimeter, and insulator. So that is the diagram for the method of mixtures. Let's see how it is used. One shall say mass ml of the liquid of the calorimeter of mass mc. So mc is the mass of the calorimeter and ml is the mass of the liquid, is noted. And their initial temperature, θ1, is noted. The specific heat capacity, Cl, of the liquid and Cc of the calorimeter are recorded. The liquid in the flask is heated until it boils, and its boiling point θ3 noted. Steam through a steam trap is passed through the liquid in the calorimeter and contents stirred until there is a measurable temperature rise. The steam is removed and the final temperature θ2 of the mixture is noted. Mass m of the condensed steam is obtained. Specific latent heat of vaporization L is now calculated from that. So it all comes from the conservation of energy, where heat loss is equal to heat gained. Heat given out is equal to heat gained. So that was part B. Now we shall go to part C. Part C says the inlet and outlet temperatures of water flowing in a continuous flow method are this and this respectively. A flow rate of 20 grams per minute is obtained when a current of this flows and a PD of this is applied. When oil, which flows in and out at the same temperature as water, is used, the flow rate obtained is this. Calculate the specific heat capacity of oil if the PD is this, if the PD of that is applied and current of that flows. So for the water experiment, change in temperature is that. the mass per second is this, but we change it in terms of seconds to give you that, because this was grams, convert to kilograms, minutes to convert to seconds, to per second. Current is that, speed is that. Then for the oil experiment, mass per second is this. Current is that, speed is that. So let C be the specific heat capacity of oil and H be the rate of heat loss to the surrounding. So by conservation of energy, we have this for the first experiment and this for the second experiment. To eliminate H, we are going to subtract the two equations. But before that, let's see the marks for this slide. So come and subtract the two equations. You will come up with that where H has been eliminated. Then you can substitute I2 V2, I1 V1, M2 change in temperature, M1 change in temperature, specific heat capacity of water. Then simplify. The whole of this gives this, then this one. Actually, the whole of this together with this, you come up with this, and this gives you this. Meaning that C will become that. And that's what they wanted. Then part D says, explain the effect of pressure on Roman 1, boiling point of a liquid, and Roman 2, melting point of ice. So when pressure increases, boiling point is raised. And why is it so? This is because boiling occurs when saturated vapor pressure is equal to external pressure. Therefore, as temperature increases, saturated vapor pressure also increases. Then Roman 2, when pressure increases, melting point lowers. Why is it so? It is because during melting, pressure weakens the intermolecular forces, making it easier for melting to occur. And that's what they wanted. So that's the analysis for this question. So now we shall go to question 6. Question 6 part A says, define the following. Roman 1, molar heat capacity of a gas at constant volume. Roman 2, molar heat capacity of a gas at constant, the first one was constant pressure, second one was constant volume. So molar heat capacity of a gas at constant pressure is the quantity of heat required to raise the temperature of 1 mole of a gas by 1 Kelvin at constant pressure. While the one at constant volume is the quantity of heat required to raise the temperature of 1 mole of a gas by 1 Kelvin at constant volume. As simple as that. So that was part A. Then part B. Derive the expression this, where Cp is the molar heat capacity of a gas at constant pressure and Cv is the molar heat capacity of a gas at constant volume, and capital R is the gas constant. So from the law of thermodynamics, that is what we have. Quantity of heat is equal to internal energy plus work done. So this work done is given by pressure times change in volume. So at constant volume, it implies that this one doesn't change, so the change is 0. That's why you have here 0, meaning that this is equal to internal energy. What about at constant pressure? At constant pressure, it means we have that. And for an ideal gas, we know that PV is equal to nRT, implying that P times change in V is equal to nR times change in temperature. So substituting for this and this, remember here, we know that internal energy is this, and from here we know that this is equal to that. So let me substitute for this and also for this and see what we get. We come up with that where this can cancel and also this can cancel, so we remain with that. So rearranging the required format, and that's what they wanted. And that's how marks will be awarded. Then part C says Roman 1, differentiate between adiabatic and isothermal expansions. Adiabatic expansion is the expansion of a gas in which no heat enters or leaves the system, while isothermal expansion is the expansion of a gas at constant temperature. Then Roman 2, state 2 examples of adiabatic changes. So we have passage of sound waves through air or sound transmission in air. Then rapid, the word rapid has to be there, rapid escape of air from a burst tire or a bursting tire or a ball. Inflating a tire or a ball. Then the compression stroke or power stroke of a 4-stroke cycle engine. Then part D says a fixed mass of an ideal gas of volume this at this expands adiabatically and its temperature falls to this. It is then compressed isothermally until the pressure returns to its original value. If the molar heat capacity at constant pressure is this, calculate the final volume after isothermal compression. So initially that is what we have. V1 is that, temperature in Kelvin form is that. So we know that Cp minus Cv is equal to capital R. To substitute for this and this to be able to get this Cv. Then from there you can get this ratio now, which is 1.41. After that, we can now say after adiabatic expansion, temperature becomes this, volume and pressure we don't know it. So TV to power ratio minus 1 is constant, so we can get this equal to this. Then we substitute for T. T1 is here, V1 is here. Then here also T2 is here, and V2 we don't know it. So simplify and make V2 the subject. Okay. Also, we know that this is equal to this for adiabatic process. So substitute, get the ratio, and so let's first leave it like that because it will help us to get our the final temperature and pressure. So after isothermal compression, we have this, but we know that P3 is equal to P1. So for the isothermal, this is the expression, then we shall come and remember that P3 is equal to P1, so as P3, put P1. Then make V3 the subject, shall come up with P2 over P1, which is similar to this. So substitute for this here, and now I can get V3. So that is V3. So they ask for final volume only. Meaning that's the answer they wanted. Then part E, Roman 1, what is saturated vapor pressure of a liquid? So this is the pressure exerted by a vapor which is in a state of dynamic equilibrium with its own liquid. Then Roman 2, describe an experiment to show that a liquid boils when its saturated vapor pressure equals the atmospheric pressure. So I need a diagram. That's a beaker. Then you have a liquid. There's a thermometer to measure temperature. We have a jet tube. Then trapped air. There is a heating element. So a jet tube with air trapped in the closed limb is placed in a water bath in a beaker. Water in the beaker is heated until it starts boiling. So water levels in the jet tube are observed to be the same. So this shows that the pressure of the trapped vapor is equal to the atmospheric pressure. So that's the question analysis for that question. Then we shall go to question 7, part A, define the following. Roman 1, temperature gradient. Roman 2, thermal conductivity. So temperature gradient is the change in temperature per unit length. Then thermal conductivity is the rate of flow of heat per unit cross-section area per unit temperature gradient. So part B, explain why a poor conductor whose thermal conductivity is to be determined must be thin and fairly of large cross-section area. So a poor conductor must be thin in order to have a measurable temperature gradient and also to reduce heat loss through the sides. So a poor conductor should also be fairly of large cross-section area in order to have adequate rate of heat flow. Then part C, with the aid of a diagram, describe how the presence of radiation is detected by a bolometer connected to a Wheatstone bridge. So we shall need a diagram. That's a bolometer, then we shall connect it to a Wheatstone bridge. That is incident infrared radiation. So a strip is connected to a Wheatstone bridge as shown above. So that's the barometer connected to a Wheatstone bridge. Then the rheostat is adjusted until the galvanometer shows no deflection. This is the rheostat. When radiation falls on the strip, they are absorbed and its temperature rises, leading to an increase in resistance. The galvanometer deflects, showing presence of a radiation. Then part D, a metal sphere whose surface acts as a black body is placed at the principal focus of a concave mirror of diameter 60 centimeters, which is directed towards the sun. If the solar radiation falling normally on the Earth is 1400 watts per square meter, and the mean temperature of the surrounding is 30 degrees Celsius, find the diameter of the sphere when the maximum temperature it attains is 1870 degrees Celsius. So first of all, cross-section area of the concave mirror is pi d squared over 4. Substitute for the diameter, you get that. Then power received by the concave mirror is this times that, which is that. So this one is for 1 square meter, but that's the area, so you multiply by the area to get the total power. Then change the temperature to Kelvin. Temperature to Kelvin. This is the formula. Power absorbed will be equal to this times that. So substitute power absorbed. This is a constant from it is usually put at the beginning of the paper. Those constants which I showed you at the beginning of the video. Stefan's constant. Then cross surface area of the sphere, and this is the difference in the fourth power of the temperatures. This and that. So it is only R which is unknown, meaning that it can be got. So this is here. Then this times this times this, you come up with this. Divide both sides by this, you come up with r squared being equal to that. Then put square root on both sides, you get the value of r. Therefore, diameter is twice the radius, which is that. So that was part D. Now shall go to part E. Part E says state 3 properties of radiant energy. So radiant energy can be reflected, it can be refracted, it can be diffracted, and it can cause an increase in temperature when absorbed by matter. So this is the question analysis for that question. Now shall go to question 8. Question 8 part A says state any 4 properties of cathode rays. One is that they travel in straight lines. They cause fluorescence in some substances like glass. They can be deflected by electric and magnetic fields. Then when they strike objects, heat is produced. They produce X-rays when they strike matter. Then shall go to part B. Show that the path of an electron projected at right angles to a uniform electric field is a parabola. So shall make a simple sketch. That's the electric field. That will be the electron before, inside, and after. So they want us to show that this path is a parabola. So from Newton's second law, F is equal to ma. So F, electric force, is electric intensity times electronic charge, mass times acceleration. Make A the subject, you come up with this. Then considering horizontal motion, x is equal to ut, meaning that t is equal to x over u. Call it equation 2. So before we go to the next slide, let's see marks for the slide. Okay, so we have got equation 1 and equation 2. Then for vertical motion, we have this because it was entirely horizontal initially, meaning there's no vertical component. That's why vertical component of initial velocity is 0. Then substitute for A and for T. Rearrange, you realize that this, the whole of it is constant. Therefore, the equation is in the form this, where K is that, hence the path of an electron in an electric field is parabolic. Why? Because this is the equation of a parabola. So that's how marks will be awarded. Then we shall go to part C. Part C says 2 metal plates, each 5 centimeters long, are held horizontally 4 centimeters apart in a vacuum, one being vertically above the other. The upper plate is at a potential of 400 volt, while the lower one is earthed. Electrons having a velocity of this enter horizontally midway between the plates and in a direction parallel to the 5 centimeter edge. Calculate the vertical deflection of the electron as it emerges from the plates. So initial velocity is that, PD is that. X is 5 centimeters, which convert to meters. D is 4 centimeters, convert to meters. So electric field intensity is V over D, separation. V is there, D is there, get that. Then I think you already derived this in part B. So my work is to come and substitute. E is here. Electronic charge is a constant. Mass is a constant. U was given, it's here. And X is here. Meaning I can get the vertical deflection. So now shall go to part D. Part D, Roman 1. With the aid of a labeled diagram, describe how specific charge of positive rays may be determined. So I need a diagram of a spectrometer. That is the photographic plate. Then shall need the momentum selector or deflection chamber. That is the first slit, second slit, and third slit. Between the second and third, we have an electric field and also a cross with a magnetic field with flux density B1. So this is a velocity selector. Here in the diffusion chamber, we also have a magnetic field only. So here it is both electric and magnetic, but here it is only magnetic. So that is the source of ions. They will pass through the slits. From here, they will be deflected now to make a circular path and hit the photographic plate. And if the radius is r, it means the diameter is 2r. So let's see how the diagram is used. 1. Ions from the source S are directed through slits S1 and S2 into the velocity selector here, having electric field intensity E and magnetic field of flux density B1. Okay, so before we go to the next slide, that's the marks for this slide. Only ions of charge 2 pass through the slit S3 undeflected with a velocity V, which is given by this electric intensity over flux density. The ions enter the deflection chamber having a uniform magnetic field of flux density B2, and these ions move in a circular path of radius r and strike the photographic plate at point say P. The centripetal force is provided by the magnetic force, implying that B2V is equal to centripetal force. So the ratio will be that. But we know that V is equal to E over B1. So substitute, you come up with this. That is what they wanted, specific charge of the ion. Then Roman 2, explain how the setup in D Roman 1 can be used to determine the abundance of isotopes. Abundant isotopes carry more energy. That's what you need to know. So therefore, on striking the photographic plate, more graphic emulsions evaporate. the corresponding line or point appears sharper, and that should be have detected them. So that's the report. Now I shall go to question 9. Question 9, part A says, what is meant by thermionic emission? So thermionic emission is the process by which loosely attached outer electrons escape from the metal surface when heated. So they escape when heated. Then part B, Roman 1. Says, sketch the anode current versus anode voltage characteristics of a thermionic diode. And Roman 2, explain the main features of the curve. So let's start with the Roman 1. We shall draw the axes and label them voltage, current. Then we can now draw the graph. Then they told us to explain the features, so we shall need label these letters at these different points to help us explain. That is saturation current. So that is Roman 1. Roman 2 we shall explain. So let's do it in the slide. So when anode voltage VA is small, the electrons emitted by the filament crowd around it and form a space charge, since their emission speeds are small. Okay. A very small anode current, IA, passes at this stage due to few electrons that are emitted with sufficient speed to reach the anode. When VA is increased, more of the electrons reach the anode, and therefore the anode current increases. When V anode voltage is sufficiently large, all the electrons emitted per second reach the anode, and therefore anode current has its saturation value Is. I think we saw it in the diagram. Therefore, along CD, further increase in anode voltage has little effect on anode current. Now we shall go to part C. Part C says, with the aid of a diagram, describe the operation of a cathode ray oscilloscope. That means you need to draw a diagram of a CRO. So we shall have a filament with low PD, then we have a cathode, then grid, then we have the anode, then the Y plates, the X plates also, graphite coating, vacuum, and the fluorescent screen. Then the earthing need to provide the potential. So this is connected here, then this one is connected here. anode is connected on this. This one is connected to the earth together with this and this and that. So the filament heats up the cathode, which emits electrons thermionically. I think we already saw what thermionic emission means. Then the grid controls the number of electrons striking the screen per second, hence controlling the brightness of the display. If I go to the next slide, let's see marks for this slide. The anode cylinder's anode cylinder A1 focuses the electrons into a fine beam, and anode cylinder A2 accelerates those electron beam onto the screen. The Y and X plates deflect the electron beam horizontally and vertically, respectively. The graphite coating conducts stray electrons to Earth, and the screen displays the beam formation by glowing. That was Roman 1. Then Roman 2, describe the use of a time base in a CRO. So the time base circuit applies a sawtooth voltage to the X plates that causes the spot to travel across the screen from left to right at a steady speed. And the spot is made to return to left rapidly as it falls to 0. So if a voltage is now applied to the Y plates, the variation of the voltage with time is now displayed on the screen. Then part D says, explain the waveform obtained by a CRO connected across the resistor R in the circuit shown in figure 3. So what waveform will be at this output? So this is a rectifier. You have to ask yourself, is it a full wave rectifier or a half wave rectifier? So let's analyze it. So that is the load voltage, and the waveform will be in that form. Meaning it is a full wave rectifier. But let's explain. So an alternating PD appears across a B. Therefore, we can have a look at it again. So this is an alternating PD. So this alternating PD will be the one which will appear here across a B. So during the positive half cycle SC waveform, point A is made positive with respect to point B. So this will be positive and this will be negative. Do you know what will happen? It means that current will flow, this conductor will conduct. So current will flow through this to that. So current flows in that direction, it flows here. Not the direction, because the direction is what matters. Okay, let's first leave those arrows there and go back and say that only diode X conducts and current flows along path A, X, R, C. I think that's what we have shown. A, X, R, C. Okay. Then what about during the negative half cycle? It is point B which is now made positive with respect to point A. So this time round, it is this which is positive and this is negative. So do you know what happens? Current will move diode Y conducts. So current will move here like this. Now at this point, there would be two options, going this side and going this side. But where does it go? It will automatically go this side. Do you know why? It is because in this direction, diode X does not conduct. So the only option is to go here like this. Now do you notice the direction? It is still downward. So only diode Y conducts and current flows along path BYRC. So in both cycles, current flows through the load R in the same direction. I think you saw that it was both same direction. Hence, SC is fully rectified. So it is a full wave rectifier, as shown in the diagram above. So that will be the waveform that will be displayed. That's the analysis for that question. And now we shall go to the last question, which is question 10. Part A says, state two characteristics of a photoelectric emission. So one, photoelectric emission is instantaneous. Then 2, photocurrent is directly proportional to intensity of incident radiation. And 3, for any metal, there is a minimum frequency below which no photo emission can occur. And 4, maximum kinetic energy of the photoelectrons is directly proportional to the frequency of the incident radiation and independent of intensity. That was part A. Then part B. Roman 1, state 3 advantages of nuclear fusion over nuclear fission as a potential source of energy. One, we shall say nuclear fusion is readily available. And 2, it is a virtually inexhaustible supply of fuel. And 3, it is none of the toxic or highly radioactive wastes are associated with fusion. That was Roman 1. Then Roman 2, why does nuclear fusion take place only at high temperatures? So high temperatures are needed to provide the nuclei with energy needed to overcome the electrostatic repulsion forces between the protons of the atoms. Then now shall go to part C. Part C says, given this information, calculate the difference in the mass between this nucleus and the sum of the masses of its nucleons. Let's first deal with that. So this one, from here I realize that there are 87 protons, and for neutrons you subtract this minus this to give you 140. And here they have given you the unified mass of proton and of neutrons and of the whole nucleus. So you come and say, from here we shall realize that these protons plus these neutrons come up with this nucleus. So substitute 87 times unified mass of a proton, 140 times unified mass of a neutron, then equal to the mass of the nucleus plus mass defect. So simplify, this gives that. So here we don't round off. Then get the mass difference to be that. Then B, how is the difference in the masses accounted for? Why is there a difference in the masses? So the total mass of all nucleons is greater than the mass of the nucleus. Therefore, the difference in mass is the measure of the binding energy of the nucleus. Then part D, state 3 uses of X-rays. So one, used to locate bone fractures, used to kill cancer cells, used to check cracks and flaws in metals, used to study crystal structures, used in security checks at the airport. Then Roman 2, explain how quantum theory provides an explanation for the photoelectric effect. So light of frequency F has particles called photons, each of energy hf. When light falls on a metal surface, each photon interacts with only one electron, giving it all or none of its energy. If the energy is equal to or greater than the work function, the photon is absorbed and an electron is emitted without a time lag. And this explains the instantaneous nature of photoelectric emission. However, if the energy of the photon is less than the work function, all of it is rejected and no emission of electrons occurs. So this accounts for the existence of the frequency of the threshold frequency. Increasing the intensity of the incident radiation increases the number of photons and more electrons are emitted per second. Thus, photocurrent is proportional to the intensity. Increase in frequency of incident radiation increases the energy of the photons. Therefore, the photoelectrons have greater maximum kinetic energy. And this explains the fact that frequency of the incident radiation is directly proportional to the maximum kinetic energy of the photoelectrons. and that will be the report for that question. And these are the general remarks you can read through. So that brings us to the end of this video. Thank you for watching, and be reminded that the next video will be on solutions to Physics Part 2 of Uneb for the year 2022. So if you have not yet subscribed, please click on the subscribe button below this video such that you can receive updates when the next video has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that you can all benefit as a family.